Hello, my name is Walter Rastler and I'm Director of Sales and Customer Support with Dlubal Software. Today we talk about special features to be more competitive with RFEM. We will learn about modeling techniques, load generation, analysis troubleshooting, and we'll see other useful features. This webinar will be recorded and put on our website for a later review. Some examples that I show today were prepared before, and I do not show all detail from the very beginning. To get started with RFEM, please take a look at our previous webinars or go through the introductory examples that I will point out at the end of this webinar. With the following examples, I want to show a small selection of the special features inside RFEM. I think those features are outstanding and can increase your productivity enormously. We will go through those simple examples and show you how quickly we can model and get to good results inside RFEM. Not all features can be covered today. I only picked out a few of them. We will have time in later webinars to show you more of the features. Before we start to work with the software itself, I'd like to point out that you have an option to ask questions in the questions box that you have on your control panel of the webinar software. My colleague Frank Sonntag, he will help me today to answer the questions. Please keep the questions short so he can answer them briefly in the text box. And if it should happen that there are so many questions we can't answer them during the webinar, please be patient. We will follow up on it after the webinar. Now I'd like to go into the live demonstration, and I will switch into the RFEM software. The first example is a simple frame, and it has it's a beam model. It has basically only the information of the beginning and ending of the member and the cross section. It has a few load cases here, live load, wind load, and a few combinations. And at the end, we'll get a ultimate limit situation result. And we can, for example, see the internal forces. And at the end, I performed a stress analysis with RF steel members. This result indicates a stress, a location here, a area here of this beam where we have a overstress. I can show this here a little bit more in detail with colors. And this area, now we have the option to increase the cross section entirely of the beam here, or we can take a closer look to this connection here, and I'd like to do this now by means of generating surfaces from this 1D beam model that we have here. So basically we're going over from a 1D beam element into a 2D surface finite element solution. And the focus will be on how to connect the 1D beam element with the 2D surfaces and how to perform the detailed analysis here. When we take a look at it here, this 1D element is now here only a visualization, but in reality it's only basically a line, and the beam element doesn't know anything about the details of this connection, but within the surface element we can do this much better. So how to do this? First of all, I have to kind of isolate this section here where there is the connection. Inside RFEM, I have the option to select a member, and then if you don't know what command you have available, it's always a good idea to use the right mouse key on the selection. Then we will divide the member at a certain distance. Please note then while I'm doing this, I see the direction of the member in the background of the selected member, and I can see here at the member end, which is this area here, I want to have a intersection at 0.5 meters. A new node is introduced and it's automatically connected, and when I take a look at the loading situation, all the loads are changed automatically and updated, so it's also on this new member. I can do the same thing again on the right side. This time I only have to hit the return key and it will automatically call the last command. And one more time here for the column, and I get here as well the new member. Here we see now the new members that have been created by this division process, and I'm selecting it, and I'm just want to have an isolated view so I can create a visibility by selected objects. Everything else is in the background and I cannot touch it or change it. In order to create a surface model from these 1D finite element members, I can use the command, again, as I said before, right mouse click, member, generate surfaces from member. And this is a unique feature in RFEM that takes the information from the cross section on a 1D member and creates automatically a 2D surface model from it. So I don't have to read all the coordinates and the thicknesses of the plates from the database. Everything is automatically done here, and it's created automatically for you. This saves you a lot of time in just getting the information about the coordinates of these nodes, and instead of modeling it manually, you can just use this very useful command. Now I have the surface model, and I also see here the details of this connection where we have, for example, the flanges that kind of interfere here with the top beam. So how to solve it? How to modify it? Well, I go to the wire mode in the rendering mode, and I select here those nodes. First of all, I want to end the flanges of the column at the bottom flange of the beam. So I select the nodes, and I say here, please move and copy or just move the nodes. Typically, I don't know the distance between here and here, but simply I can grab it from the model. I just click on the two nodes and I get the displacement vector. I can set to 0 the dx vector and only use the dc distance. On OK, everything is moved on the same level as the bottom flange. So if I check this, I have here C minus 3.910, and here is also minus 3.910. Automatically, RFEM realizes that there is here a node in the same plane and will automatically mesh it. Okay, the next thing I have to solve is I have to think about how I can connect the 1D member with the new 2D surfaces. Typically, it's just on one node here, but it's not so good because it will create a singular effect, and a little bit better solution is if we could have here a rigid end plate that would transfer the forces more smoothly into the flange and into the web. So how to do this? I simply create here a new surface by polygon. polygon means I have to select the boundary nodes. From the surface types, I pick rigid, which is an automatic rigid plate. And on OK, I then can select all the boundary nodes that I need to describe this rigid surface. Once it finds an enclosed loop, it will create the rigid surface. I do the same thing on this end. And one more time here at the bottom. You can see a surface is marked by a dashed line inside the area. You can switch from the wire model to the solid model, or you can switch to the solid transparent display model. The transparent display model has the advantage I can see through and I can grab through, for example, this web here, which I cannot do if I have the solid model. It's done that the nodes are drawn in foreground, but basically I cannot see everything in the background. So sometimes it's better to work with the transparent model, or sometimes it's also better to work with the even wireframe model. So everything is at your fingertips and you can change it as you like. Okay, I go back and I cancel my visibility mode. Can change to the full model, and I see here we have the same geometry that's just going straight over to the surface model. By default, we're displaying the surfaces only at the center plane. We don't show any thickness. If you want to show the thickness of the plates, you go to the display navigator and you go here and you say rendering model. We can go here to surfaces and we say filled inclusive thickness, and then we see also the thicknesses, or we can have even a wire frame around the edges, and you see we exactly match the thicknesses of the original cross section. Okay, now we are basically done with transition from a 1D element to a 2D surface element. What we have to think about is how do I mesh these surfaces? At calculate FE mesh settings, you can set the target length of the finite elements, which is set here to 25 millimeters. We have also options here for mesh refinements, but in general, you don't really have to change anything here. The most important setting is here the target length. I can regenerate the mesh on OK. If I do so, a mesh is created, and we see now here a nice mesh which has rectangular surfaces, and it also has a relatively suitable density, so there are several mesh cells along the flange, for example. Okay, with this we can try to run the analysis. I display the results, and RFEM asked me, should I calculate? And I say yes. And after a few seconds, I see my results here. I see my bending moment. I see in the result navigator here, bending moment, axial force, shear force, and so on. I can change the display of the diagram in the display tree here, and I navigate to results, and I can say to colored, which is basically the default what we have. And also I have options for surfaces. At this moment we have no more moment diagrams as we have for beams, so it's a little bit more complex to analyze the results. We see here there is a patchwork basically display of the results. Which results are we seeing? It's mx, so it's the surface internal force, bending moment mx, my, and so on, and you can switch here. You can also display the stresses, equivalent stress, and so on. So why we have here this rough patchwork display? Actually, this is not default. It's from a previous setting I made when I was preparing this model. Default would be continuous within surface. So let me explain that briefly to you. Once we have a surface model, we have an algorithm that smooths the pretty rough results on each finite element mesh node. So each mesh node here on each corner of the mesh of the finite element has an individual value. We also are able to grab the results on any location along a surface. So we're doing interpolation. And this interpolation is continuous within surfaces. So when there is a boundary line of a surface, we will not average the results from one surface to the other one. It is important to know this. For example, if you have a difference in thickness of the surface and you have a stress on one side and a stress on the other side, you cannot just average out and the stresses. So there has to be a small discontinuity in the stresses. So therefore we cannot just smooth everything and kind of make average values from surface to surface. So we have to control this how we do it. And there are several options. I'll come back to constant on elements later because we'll have to do a plastic design and there will be some differences. Okay, let's see the result of the ultimate limit state combination. When I run the analysis here, I get the local stresses on each finite element, but this time it takes into account the local condition here. There's a lot of pressure, tension maybe, and the force is concentrated here at the point where we connect to the web. We see here there's an equivalent stress. I can go again to the stress results here. I can look at sigma x, sigma y. I can also look at the membrane stresses, for example. So we see there's tension on the top and then there is compression on the yellow or almost. There's also tension here, but what we have here, the green is compression, for example. Yeah. So, and we can take a look at the equivalent stress, sigma equivalent max of von Mises. So we see here the maximum value is 94, which is quite high for a regular mild seal. We have a yield stress of about 24. So there is some problem. So let's say everything with this blue color here seems to be okay. I can also show the local values here. RFEM has an algorithm in here that shows only selected values and not all the values. If you do not take care of stuff like this, you get things like you get results on all the values here of and you will not see all the results because you get so many values that you don't know which one are the maximum or the minimum values. So if you say extreme values, it will give you a nice selection. So you can control this here very nicely and smoothly with this result 3. Okay, so it's clear that we have here a problem and we cannot say it's safe. So how to do a plastic design? When we do a plastic design, we have to do a nonlinear analysis. It will reduce the stiffness of individual finite elements, and it will also therefore redistribute the forces. And the way how the software works, it compares the existing stress with the limit stress for the yield stress of the material, and then has an algorithm in there that reduces the stiffness and the elasticity modulus of those elements. Because we can only reduce the stiffness of the entire finite element, we cannot evaluate, or we should not evaluate the result separately in each node of the finite element. We should see it as, we should average it on the finite element as a constant. So, okay, what I do? First of all, we have clear. First, we have to select something, and then we can edit it. Just double-click on the selection, and then we can create a new material. We create a new material. I pick it from the library. I can choose from my favorites, which I have already here, steel and some concrete materials that I typically use. I use mild steel, and here I can choose the material model. By default, we use isotropic linear elastic, but for this analysis, I use isotropic plastic 2D, 3D. This option you have if you have the additional module RF, MAT, and L. So with this material model, I can set the yield strength and also some strain hardening modulus. So the material model will analyze the strain and then set the elasticity modulus according to this curve. Okay, so at the end I should not get any bigger average value per finite element than 23.5. I use this material, and of course I have to delete the results. So I can check in the view tree visually, because now I know it, but I cannot see it. Did I do everything correct? But I can use the view tree here to show surfaces by material, or you can show members by material. So or even a better way is to use the tables here. If I select here one entry in the tables are also a very powerful thing in RFEM. The selection is synchronized. So whenever I click here, I see which members use steel, the first material, which one use the isotropic plastic element. Okay, if I click here, everything else is disabled because it will enable or disable the active view. I can click here, so it is disabled as well. I can only work with the material number 1. So I have an option to check my input visually. Okay, it's done, and I run the analysis. First of all, I want to do something else. I forgot something. I also have now the option to, for example, change the thickness of an individual plate here. I can select it. Multi-selection is possible with pressing the Control or Shift key. I can rotate it. Actually, if you rotate it, you use the Alt key. Usually when I rotate, I can use the Control key and the wheel of the mouse, and I can rotate it really nicely. Sometimes rotation is not what I cannot see what I want to see, because the center of rotation is somewhere else. If I want to rotate about a certain node, I can use the Alt key and the wheel of the mouse, and it will rotate around the selected node. Okay, I've lost my selection now, and I have to do it again. 1, 2, 3, 4, 5, 6, and the other 2. So all the selected plates, I want to change thickness to 20 millimeters. Okay. Okay. Also, I can display now surfaces by geometry. So, or by actually not by geometry, by thickness. So I can hide and show certain certain surfaces actually. So let me change this by material, So if I want to see only certain my 20 millimeters, so only those are active. Okay, cancel the visibility and we run the analysis. Now we do a plastic analysis, so there will be a few more iterations. You can follow the iteration process. You can see how many iterations are here. It's all also in a log file, so you can see it in the printout report if you reach the convergence or not, or how many iterations have been done. You can see also a small diagram that shows you, okay, is there some problem? Is it moving away? Is it converging or not? Everything can be recorded and printed actually afterwards. We see here now the results, and I'm interested especially in the surface results. We see here now we have the equivalent stress 33, so it's drastically smaller, but as I said before, because we are reducing the stiffness only as a constant per finite element, we should look at the results only in the distribution constant by element. So if I see this, then I have 23.49 as the maximum sigma equivalent von Mises. We see here the red areas where we have actually the stress. It's a slight bigger area than we saw beforehand, where we thought there was an extra overstress. This is due to the redistribution of the forces, because we now have also a different stiffness through the plastification. Also, I can take a look at the not only the stresses, but also the strains, because I have to make sure that I have not the endless strain in the material. The material can take only a certain amount of deformation. So I have also to know the strains, and I see here the maximum values of the strains, and it's 0.1% for the maximum here in the red. Also of interesting is the so-called non-linearity rate. I want to see the elements that use a non-linearity, that are plastifying, so I can show this also by this criterion. If you want to have even more condensed results and at the points of interest, you can create a mesh refinement and condense the results even more there. Okay, I think this is it for the first example. My intention was to show you first how quickly we can model the transition from a 1D element into a 2D surface based element based model, and how quickly we can do a plastic design. It will help you to do a more safe design, and will limit the use of material only on that location where you actually need it. The second example I'm going to show you now is maybe not so much breathtaking example. It's a continuous beam, and it consists out of 3 members, has 2 load, or actually 4 load cases, and several combinations. Also, I have a design case in the additional module RF Timber Pro that allows you to do a design of timber structures for beams according to Eurocode or other codes, including stability and capacity checks. And when I take a look at it, we have about maximum design ratio of 95%. Okay, why I'm showing you this? Well, RFEM is a very powerful, large program typically used for frameworks that consist out of maybe many thousand members or many hundreds of surfaces and solids. Typically, often people use individual programs for this type of structures that are small, that are parametric, that are doing just this job and nothing else. What you have to do is you have to buy a second program, you have to work with a different vendor, you have to work in a different user environment, you have a different look and feel of the software and look and feel of your printout report. I want to show you how you can also handle and give you an idea how you can also handle such structures quickly, and not only such structures, also other small problems that you have inside RFEM. Because this model has some intelligence inside. I go to edit and edit my parameters. This model has parameters, and the parameters are A, this is the span A, B with span B, C is span C. I have self-weight and live load. If I go back and go to some results, I see my loads. So now I can use those parameters and change them. Go, for example, 5, maybe let's have 8 at the end, and a few different loads. I press apply and everything is updated. Maybe the span at the end is too long. I want to have it maybe not 8 meters, but some different distance. Then I can change it quickly and update everything. Okay, now there is some saving going on in the background. Just give me a second. So here we go. I can put it to 6 and update it again. Or the load maybe to 4 and update it. Notice the value will change here. That was wrong button. 4, update. Okay, once I have this done, I can calculate everything, and everything will be updated, including my concrete, including my timber results, including the internal forces and everything else I have prepared. The good thing about this is I have also a printout report in this parametric model. So I set it up once and then I change my parameters, and within a few mouse clicks I can change it to any continuous beam that I want, and everything will be automatically updated. If I go to the data navigator, I can find here my printout reports, and in this printout report I have a shorter and a longer edition. And if I open the printout report, it consists out of 11 pages, which has the most important pictures and the most important tables automatically prepared. And I can go and I can say view, zoom 2 pages, or I can see a little bit better. We can go here and look at the support reactions, and pictures will be updated with the current result. Also we see here shear forces, bending moment, deflections. Everything you can select, all the details are here, and here we have our utilization ratio. So very, very quickly, if I want to change it, I close it. Oh, something else is wrong. I want to do my parameter, I change it, and I say, okay, let's go back. C should be only 4 meters, and this should be also okay. I click OK, calculate all, and everything will be updated, and I can take a quick look again at the printout report. It will also be updated. So very quick way to modify the structure to make things parametric. Next, we'll take a look how to make such a parametric model, and you will see it's a very simple thing, and you can quickly do it also yourself and learn it yourself. Everything what you see here, all the technology is included into the main RFEM program, no additional module needed. So you get this, when you buy RFEM, you get this parametric modeling automatically with it. So there's a lot of power that's extra inside RFEM that people sometimes don't even know about, and I think this is a very, very good advantage for you working in your office. So we see now we have the updated model. Somewhere I think I have even dimensions, and we see here there is 4 meters only. We have your member numbering and so on. Okay, how to create such a model? Quickly, I create a new structure. I want to have it in a 2D, as a 2D model. So the RFEM 3D allows you to work also in a 2D environment. And I call it one continue. Okay. I can now manually draw such continuous beams, or I can use another tool, generate models, continuous beam. Also standard content of RFEM. You can set here the number of spans, you can set here the distances. I want to create load cases, self-weight, load magnitude 3 kilonewton per meter, variable loads 5 kilonewton per meter as a default. I want to create a cross-section, so I can choose here from the cross-section type, rectangle, and we say here 300 millimeters by 500 maybe. And also I'll choose from materials that I have here. Some is already prepared here. You can change it, go wherever you want to, and use whatever type of material you have. It comes all with the software. Okay. Okay. And additionally, I also get all the cross-section information. I can see all the stress points. Everything is clear visually there. You can print all those things. You get all the details that you need, and not only the geometrical information. Okay, on another okay, I get here my continuous beam. I hide the grid because it kind of is disturbing me. I see here the loads, my load cases, and so on. When I opened the structure, I decided to create a standard, according to standard load cases. So we use here, for example, Eurocode, but we also have other codes, American codes, British codes, Chinese codes, Indian codes, and so on. And we can here then set the national annex if available, and we can automatically create combinations, load combinations. I choose this option here because that will make my life more simple. I go to the load table here, and I see here that we have our 4 load cases. You see here everything is also synchronized, so whenever you click on it, you see automatically what happens in the graphic here, and you know exactly what we talk about. We can create automatically load combinations and see here the load combinations. Actually, I forgot to disable here some combination expressions. I only want to have the combinations for ultimate limit state. So altogether we have 8 combinations, for example, that are possible. Okay, it is created. You can do this with any other model. You don't have to do a continuous beam. You can, this way you can manually change everything. It is possible to manipulate things. You can say here, okay, I want to have it 16, no problem. But how to make it parametric? Well, first I need some parameters. If you are in the structure table, model data, you find here the button edit parameters, or you find here edit parameters. So I define my first parameter. Then I say span 1. It's of type length. It should be maybe 3 meters. span mid should be also of type lengths and 4 meters. And span 2 also of type lengths 5 meters. Then I'd like to have load case self-weight. This is not of type length but of type line force. By default it should be 1 kilonewton per meter. And live load, also line force, maybe by default 3 kilonewton per meter. Those are the parameters I want to choose from. Fine. I say OK. Now I need to change the coordinates depending on the parameter. If I want to change a coordinate, I double click on the node. Here I have the actual coordinate in X now. If I click on the right corner here with the little triangle button, I get further options. And here I can edit formula. And instead of taking it from the text box here, the coordinate X, I want it from the parameter span 1. Double click, done. So it changes to 3 meters and there's a little formula sign similar like it is in Excel. Okay, 3 meters. The next coordinate, quite simple, same way. Edit formula, span 1 plus midspan, 7 meters. Okay, okay. The third coordinate, 16, a little bit much. Edit formula, it remembers the last input plus span 2. Okay, okay. Everything follows. If I want to change something now, I can test it out. 4, let's make it all even. 4, apply, it works. Hooray. We can also draw here some dimensions. So we see that we are doing it correctly. Okay, what is left are the loads. So I'll choose one load case. I select my loads. Double click on the loads. Here I have the same buttons, edit formula. It should be my self-weight. Okay, okay. And then I go through the other load cases. Now I have to do it a little bit more often because I have 3 load cases. Live, okay, okay. One more. Edit formulas. It's already there. I just have to confirm. And last one. Okay. Okay. So, and this way I'm done and I can change my parameters. See how it works? So 5, load case 2, load case 5. Okay, okay. You see here it changed because we have here in this combination we have 1.5 load case 2. So 5 times 1.5 is 2.7. If you want to see the real value, you go here and you just select the load cases without safety factors. So everything seems to work, and we have done our parametric model. So if I want to do this 2 and 2, okay, done. Calculate all, everything will be analyzed and calculated and updated. If I prepare my models one time, I can quickly change them in the way I want them, and it's a very powerful thing. In fact, you do not have to do everything by yourself. When you buy Dlubal software, you get a tremendous amount of already parametric sections, parametric structures with you. You can change things. There is all kinds of structures that we have here. We have space frames. We have global trust products, which is prepared parts that you can buy on stock from manufacturers of stage constructions, for example. So they are all parametric. If you use this, we have to go back to RFEM. If If I open something like this, for example, it will open in a preview. You see here, I can change the length. I can even show the parameters. If I change the length here to, you see how it will change. It's all parametric, and you can use these things and import them to your existing structure. So I can say I want to glue it on a node on an existing structure or with some spacing in between. You can set the cross sections and so on. So very powerful thing that already comes with RFEM already at no extra cost. So with a big program, we can make a very effective analysis of a small problem. We'll see more about the parametric modeling later. It's a very flexible way to analyze things, and basically you can customize RFEM with, if you want so, with individual modules of generators. The next example I want to show you is about intersections. Also a great example of how powerful parametric models can be. What we see here is part of a, could be of a larger truss. We have here pipe cross section and another couple struts that connect to the main beam here, main pipe, and it's a surface model, so it's not a beam model in this time, and it's connected here, so it has the intersection line exactly between where the one strut connects to the main pipe here. So this model is also parametric. I have here also parameters. I did that. There was not a lot of work. This time I can, for example, change the angles. I can work with sinus, cosine, and so on. I can say, okay, 30 degrees. I can say, there's even loads here, and on the other side, maybe 50 degrees. So I can apply the changes, and you see how it changes. And the clue on the whole thing is that it also updates this intersection of the two cross sections here. Also, if I change the diameter, actually you have to do it a little bit different. Right mouse click, edit component. If I change the pipe here, to 0.4, for example, meter, okay, it's intelligent and it will automatically update these intersection lines. So it's a very powerful thing. It's an intelligent object. Next, I will show you how to create such an intersection. I have prepared, to speed it up a little bit, a small model that only has now the center lines of those pipes. How to create pipes? Well, you have to first have the center line, and then you choose here from this button line here, pipe. Material, I chose steel again. Thickness, I set 10 millimeters wall thickness, and then I go to pipe here and I set the diameter. And I can use here maybe 300 millimeters. Okay, and now I can just click on the line, and automatically it will create the surface here. And you have the pipe here as a surface model. Next, I'll do the other two pipes. Same way. This time I only choose a little bit smaller, 180 millimeters. This one and this one. Now I have the parent objects, I would say, the two surfaces, but I don't have yet the intersection line. How to do this? Well, quite simple. As I said at the beginning, if you don't know what to do, you use the right mouse key on the selection. I want to do something with surfaces. I want to create an intersection. Okay. And here we are, we see the intersection lines. But I want to get rid of the internal part of those struts here. So how to do that? Well, this time we work with the navigation tree on the left. We go to the data tree here. I want to do something with surfaces, so I check here surfaces. And here we see components. Well, if I click on it, basically I see right away where I am at. So it's also very, very powerful, very important to see what is selected. Pipe 10, 11, 10, 12 doesn't say nothing, but if you see it in the graphic, you know exactly where you are. Okay, now you see here active, I can obviously deactivate some things. This part I want to weld it on the outside here of the main pipe. This one I want to, but I don't want this one. So if you don't know what to do, right mouse click. Deactivate component. Here we go. This one I need, this one I don't need. Deactivate component. This one I need. Now I can rotate and I can look through. Everything seems to be okay. I can also take a look in here. Looks great. Okay, now we want to see how we can analyze this model. Well, I need to have some supports. I can apply the same principle as before, and I can make like an end cap on this pipe and then put in the center a support node. This time I select boundary lines. Again, I select rigid of surface type, and because I select boundary lines and there is only one, I just have a single click to assign this surface. Okay, because now I have kind of a connection between my center node and the wall of the pipe, it's easy for me. I can here create a new nodal support. I use a new type, fixed in all directions, restrained about X. Okay, okay, and I just assign it to the individual nodes. Okay, if I want to, I can create some load cases. I'll use my self-weight. Automatically calculates the self-weight of the structure, and I run the analysis. First of all, I can't forget to check the finite element mesh. I go to my element mesh setting. Here I use maybe 100 millimeter as mesh target length. And we calculate and generate the finite element mesh. We can see here, we'll see better when we have the results. We run the results. It's a linear analysis by default. And we get here first deformation, which is very small here and therefore not impressive. But we also get the surface internal forces. We can again display the stresses, and we see here where we have the problematic zones, and everything can be analyzed again as before. So very powerful thing. I do not do the parameterization here. We have seen that before. Important is to know, okay, we can do those intersections. It does not only work with pipes. You can intersect any free form shape with another one. If you change any of the parent objects, the child objects will follow, the components will follow, and you don't have to recalculate your meshing and everything. Everything will be automatic. So very intelligent object and very simple to handle and very flexible. Next example. Next example is a typical engineering problem where we have to deal with singularities. This time we deal with concrete. So I'm looking at this model here now, which is a simple plate made from, this time from concrete, thickness 200 millimeters, and I have here some point supports at different in a different distance, grid arranged, kind of. And when I run, I have a couple of load cases again. Doesn't have to be many. It just needs to be showing the principal work with it. So there's self-weight and then there's a live load, and I have a few combinations, this time linear. Ultimate limit state results are, for example, we can see here the mx value, my value, and so on, or we can take a look at the deformations. Okay, what I like to point out is a typical problem, which are singularities. And if I take a look at the maybe equivalent stress or forces, then you see here everything. There's high concentrations of stresses actually here on those points. So first of all, how to find singular points, how to find problematic points. Well, typically it's locations where there are high stress gradients. So if you make the mesh dense, you will get an infinitive high value, and it's very steep. You will have a very steep angle, the change from one finite element to the other one. I can show you this. For example, if I make a section, a longitudinal section. Let me do this first. Create a new longitudinal section, and we do this from here to here, and we see here now the results. We see here a result diagram, which is also a very, very powerful feature in RFEM. You can choose which type of result you want to see. For example, bending moment in one and the other direction. You can also choose your load case you want to see. Yeah. So we see here very steep increase at the points of the supports, and these are problems at the value you can increase it if you make a more dense mesh. And if you do the design here, you'll get a very high value of reinforcement. Let me save this. I call it mid. Okay. Okay. You can see here the values are. You can see the results here on this section in the center here. I'll make it a little bit nicer for you. In the display navigator, you have the option to set all the settings for the results here. And I want to see not differences, I want to see isobands and not those values. Here we go. So you can see here, and maybe we choose one combination. You can see here the peak values, for example, of the result I'm selecting here, sigma x or mx, for example. You can see that here. Okay. How to find, sometimes it's not clear where there's a singularity, how to find it. Well, you first have to select a stress as a result. Let's go to sigma equivalent, and then I can show the differences, which is basically the stress gradient. And it will visualize me where we have a very high gradient. So the stress gradient, where it is red, is 60%. So the increase from one element to the other one is 60%. So it's a location where there is a lot of increase in these values, where we have those peaks. And those are typically the problematic places. Here it's clear because it's a point supported slab, and where the point supports are located, you see the singularities. But in other structures it's not so clear, but you can find it in this way. Okay, how to handle those things? I go back to isobands and I change it to mx maybe. How to handle those situations? Now, how to handle singularities? There are two ways, and I'm going to show you the two options we have. First of all, we can do following. We can select one node here, and I create a new support type. Here I create an elastic support, so everything which is rigid is not good. So if it's elastic, it's better. But how to find out the elasticity of such a support? RFEM has a tool that allows you to calculate such stiffness from the geometry of a column. So we have, for example, a circular type, diameter 500 millimeters, length 5 meters. We can choose the material, and we see here automatically the spring constants for this column. We have the option to have elastic surface foundation, so the model internally will be an elastic supported surface. We can have an elastic node, so it's a point support but a spring constant underneath, or we have a node with adapted finite element mesh, so it will also kind of narrow down the result around the column with the finite element mesh change. I stay with the first option because I think it's the most effective one. But it's up to you what you choose. I click OK and OK again. Of course, we need to delete the results. And we see here we have one area here where we have a different support symbol. I'll run the analysis. And we'll see the difference. First of all, the results are hidden inside the column because we assume inside the columns those results are not so relevant. Often it's standard practice that you make the design at the edge of the column. So we get the values at the edge of the column. Also, we can compare, for example, I have made here, I didn't explain to you, we have here a concrete surface case. So we did actually a design for concrete, which is here in the module RF concrete surfaces that analyzes the structure according, for example, Eurocode, and I get a reinforcement for this structure. If I do this, I can look at it graphically. I can see here RF concrete surfaces, and I get a result, and I hide the other values. I get a result value of 38 centimeters square by meter on this peak, and 22 only on this peak. So you see, with the modified support, I reduce the result in the needed reinforcement dramatically. So this is one way how we can handle this problem. Next way how to handle this problem is called average region. In RFEM 5, this is a new feature. I can enter here average regions. If I create a new average region, I have to enter a name. I have to select a surface where I want to use the averaging region. I can select whether it should be a rectangle, a circle, or an ellipse. I stick with a rectangle, with a circle, and I'll place it right above this support. The dimension, I'll choose about 2 to 2.5 times the thickness. So we have 200 millimeters, maybe 3 times, so it's 0.6 meters as an averaging area around the column. I will average in both directions. I click OK, and we'll now run the analysis again. You see, we we had something like 36 square centimeters or 38. Now we have only 30. And I'll have to explain a little bit more because I have to go into the other direction. So this is reinforcement in direction 1, reinforcement in direction 2. You see here there's the average impact. Basically, I can show and hide the averaged results. Maybe if I go back to the combination. Hang on. Combination this way. Data, results, sigma x averaging out. Okay, sorry. Okay, one more time. Calculate all. Okay, this is something I didn't want to see now. Okay, I'll need some more stresses, bending moments. So let's see what happens now. Where are my averages? Surface diagrams. Sections. One more time. These bands are here. Averaging. Averaging display. Here we go. Average region in and out. So now let's see the result one more time in the sections. Display sections. All values. Sections. Here we go. Okay. And if I show the average region, I need, there is no difference now because I need to average in the different direction. Okay, I'll show you one more thing regarding the result diagrams. Those are also objects that I can, and we come back to the averaging after that I can move and copy. I press the left mouse key, control key, and the left mouse key, wait a little bit, it will copy it, and then I can drag and drop it to the location I want it. So for example here. Same thing, I can create a new average region on the other direction, a new result diagram in the other direction. You see here the result course again. I save it and I call it in this case A. Okay. Okay. And it's in the other direction. Again, I'll copy it a few times from one location. First select it and then copy it from here to here. Something didn't work. Sometimes if you have trouble, you can also do it this way. You select it, you say copy, one copy, and you copy it from here to here, for example. Okay, it's an object like anything else. Yeah, you can copy it from one option, from one end to the other one. Also, now I try it again one more time. Copy, and I move it to here, for example. You can edit it. You can say it should be at 5.5 meter. Okay, and it will be exactly where you want it. So actually what I wanted to see here is this result. I'll go back to 0, and now we show the average region again. Self-weight. Let's go to the concrete results. In concrete itself, you have to select also in the details that you want to design the average internal forces. The sign is here. Okay, and I run the analysis again. So I used the smoothed results, and then I should be able to display them here. Results. I need now ISO bands, and I did something wrong now. Here we go. Now we see here the averaged results in RF concrete. So from 38 to 27 we have a tremendous reduction of the average result. And also it's a good thing how to make a documentation with this design sections, with these result sections. Let me copy one more time from here to here. One more, maybe also here. Go to here. Okay. So instead of displaying the entire forces, you can also use this display as a good way to display the results. For example, I go back to self-weight. You can use this, or you can use ISO bands, or you can also use only show nothing and use only the sections. I can hide the grid, and this way I have also a nice way how to get the documentation of the results. So I print the graphic, for example, as a mass print into the printout report, and I can select I want this result, this view for all those results, MX and Y and so on, for all load cases. Okay, 50% of the page should be used for one graphic, and I will open the printout report after that. I'll open a new printout report, and it will give me the results. Nicely prepared with a nice set of graphics that I can look at, and 2 graphics on one page. Takes some time to update the pictures, but now you can see how nicely everything is there, and you get all the peak values correctly, and not everything is just written above each other, so it's really nicely prepared, automatically prepared. Also a feature that saves you a lot of time when working with it. I accidentally put here a dimension. I can delete it, for example. It will be gone then also from the printout report. Everything is updated automatically. Okay, this was how to work with result diagrams, how to use them for printing, how to handle singularities with the column feature as the point support, and with the average region that I've been showing to you. Yeah? Next, I'd like to show a few more things regarding tracking of problems. I have prepared another model. Again, it's parametric, and this model is a steel hall. I've made it completely parametric. You can edit the parameters here, and you can say, okay, spacing 6 meters should be 7, 5 meter 80 should be 6, the angle of the roof should be 20, and I can update the view. Everything is parametric. Since we have load generators for snow load and self-weight, snow load, wind load, for example, and they are following the structure, we have here a really parametric model. So if I change the spacing to 6 meters, for example, and I say apply, you see how the load will change also, because it follows the geometry. So very powerful tool. Okay, I run the analysis here. I have 6 load cases, also including imperfections like drift and camber. And I'll run the combination 16, which is self-weight, snow, and an imperfection, and I run the analysis. When I do this, sometimes if you work with finite elements, you see that there are problems with stability. It's a non-linear analysis, theory second order. We check also stability. And I get a warning that something went wrong, but I don't know what is wrong. There's an instability in here, but I don't know where the problem is. So how to find it? Well, I can try to run a load case on a smaller load level, for example, self-weight. If it is a stability problem, I can use, for example, I can start with a linear analysis. And basically, or typically in our software, load cases are linear. You can set it up as you like, but by default, we run them as linear. So you can set it up, load case, 1 calculation parameter, geometrically linear. Okay, so the model is connected, it works fine, it's there, but it's a stability problem. It's second order theory gives me an error. So how to find it? You can use the additional module RF stability for this, and I start it, and I analyze the an eigenvalue. I analyze based on the load case 1, the eigenmode of this structure. I import the actual forces of load case 1 into this eigenvalue solver. I run the analysis of 4 eigenvalues, and I get a critical load factor, which is the factor that I can apply to this load case. That was the basis of my analysis, and I can basically linearly extrapolated 3 times 169 times the load on this structure that I have now in order to be stable. This is one number that shows me how far I am away from instability, from the point of instability. But I still don't know what's the problem. So for this, I have to look at my shape eigenvector mode. And you see here, there is some column that's pending for the first eigenvector, second eigenvector, it's also here on the other side. And the third mode is here, the fourth mode is here. So this is most likely where I have a problem, because to this critical load factor, this mode belongs. Okay, what I'll do now is I'll select, I go to the cross sections here, and I have a list of cross sections, and I select one of these members columns that bends, and I see when I go here, I use my synchronization, I see all those failing members are made from the same cross section. If I change the cross section to 200, then I want to see the effect of the to the critical load factor to it. I run the analysis again, because now this first failing mode should not appear anymore, because I made the cross section bigger. So what we see now, we see a much higher eigenvector, a much higher critical load factor, and we see also a different failing mode. So now if something fails, it goes this direction at a load factor of 28. Then we have the other critical load factor is the typical buckling mode of the frames. And the third one, now here we have this column. So at 31, so before it was 10 times higher load factor, now by increasing those columns. And now I can try if I can do also my second order analysis. So I run this load case 16 and get my results, and now there should be no more problem. So by using this stability module, I can find the problem, the location of my problem. If I get a stability message inside the software, I typically do not know where the problem is, but with the use of this eigen mode and the RF stability module, I can find this, and it can tell me more about the stiffness distribution in this structure. Okay, another final small example I have here with the let me see, plausibility check. I started with a small example. I will end with a small example. Again, we have this, looks like the same frame like we had at the beginning. Everything looks just fine. I have a self-weight load case here. I run the analysis and I have a problem. The stiffness matrix is singular, structure is unstable. Well, the good thing about it is RFEM tells me with an arrow where maybe the problem is, and I can go and look. It's one good thing. I already get the degree of freedom, direction X, and the node, the finite element node. So here, but I don't see anything, looks still okay. What's the problem? For this, I can use the plausibility check or the model check. And I have several features here. And one is to find identical nodes. And here I can set a tolerance where I find identical nodes. So if there are nodes that are lying close together, that can cause a problem in meshing, or maybe I'm not aware that there are two nodes that are close together, I can find it. In order to find the problem here, I change the tolerance to 5 millimeters. And I check it now, and now I see there are groups of identical nodes. And I can now do nothing with it, or I can say, please create visibility of each group. So the selection here, those nodes will be put into a certain visibility. 2 new visibilities have been created. I go to Fuse, Visibilities. So now I can select nodes 4 and 7, which are here. And I see, if I press isometric view, I see that there is a big difference. Now it is, I change the visibility. Okay, and you can see here is the problem. In here. So I have to go down closer, and I see here now there is a problem. We have the coordinates, we have 1 millimeter of difference. And the same is on the other end of the structure, where we have here the same problem. Okay, how to solve it? I can either drag and drop the node. Also, not every software can just drag and drop such a node and connect it this way. Or I can use again the tool model check identical nodes. Check again. And here I can use unite nodes, supports, and delete unused nodes. So if I check this option, I click apply, you watch here, you'll see how it connects automatically. So RFEM saves you a lot of time in finding those modeling errors that can occur, for example, when you import from a not so perfect DXF file, or when you're just modeling rapidly and you have a big model and you have to find those little problems. You have tools that help you find those things. Okay, this is what I wanted to show you today in this webinar. We've seen the rapid generation of FEM models from 1D beams. This way you can handle steel details in a very fast way and very effective. You can solve problem zones where beams are not enough. We also seen parametric modeling, how to model simple structures and parameterize them. It's a great way for fast and flexible reaction to changes. You save in buying other software because you also can handle big and small problems inside RFEM. And you have an all-in-one solution because you use one software for all your problems. Also, we saw how to create intersections and how intelligent those objects are. With they change intelligently after you change the parent object. We also learned how to handle singularities. We have seen that RFEM is not a scientific program, but covers the problems of daily engineering work, and it uses the tools and the methods that typically are used by engineers, and it helps you to get practical solutions. Result diagrams are also a good way to show the result and present the result in your printout report. RFEM is not a scientific software. It has a lot of powerful solvers and scientific solutions inside, but it's made for engineers and for daily practice work for engineers, and not so much for the scientific use. So therefore it includes all those things that we have seen here, and I think it will increase the productivity of working, of solving your engineering problems, and rather than dealing with facts like modeling and how to get coordinates of measures and so on. RFEM can really help you with this. Okay. Before we end this webinar, I'd like to point out our website. We have here options to look at videos and to apply for newsletters. You can visit us at certain events and conferences. You find this all on our website. We have here also the links to follow us on our social media channels. I'd like to point out especially the blog, where you find daily messages that we post here, and we can search here inside the blog, and here you find, for example, also a short hint how to create an intersection. You can read about this, so it's a good source of information. Most important is the trial version of RFEM that you can download here. It's a 30-day fully functional trial version. Please take a look at it. We have also a special page for beginners where it has information where to find introductory examples, where to find tutorials, and how to get help with learning RFEM. I think it's very little time you have to invest to get started with RFEM. I would say if you take a couple of hours, you will have your first results, and you can basically install and start to work with it. There is not a lot of training required for RFEM. This is one of our most important advantages, I would say, the user friendliness, the easy to learn software. Before we end the webinar, I'd like to thank Frank Sonntag for answering the questions. I hope everything has been answered to your pleasure and everything is clear. If you have any more questions, do not hesitate to contact us. Send us an email at info@dlubal.com. We gladly answer your questions also the next days and later. I'd like to point out the next webinar that's on our calendar on September 19th. We will handle RFEM and BIM integration with Tekla structures. You can register at the website dlubal.com webinars, ASPX, and you find here also, because it's always a question, you find here also the previous webinars and the recordings. You can watch with your credentials, you can watch the webinar again. There are several webinars also from last year that you can watch here. And you find all the upcoming webinars on this page. We have different webinars for Germany and for in different languages, in German and in English, and we will also provide more languages in future. Please go to the page with your preferred language and you can follow us. Thank you for your time today, and also thanks again to Frank Sonntag for answering the questions. Thank you for participating. I'll hope it was good invested time for you, and I would be very happy if I could see you again on one of our future webinars. Bye-bye.